Hi, welcome to the seventh session on infinite series. Today, I'm going to prove an interesting result which I said yesterday. Look at the standard alternating series, summation minus 1 to the power n minus 1 by n. Okay, we know it is convergent, we had already seen it. Now I'm going to say if I rearrange and then sum it, the new series will have sum which is half of the original sum. Okay, that shows why with infinite series one has to be very careful. Okay, after that we will also talk about a series which is convergent but not absolutely convergent. What are the consequences? The last result will be if a series is absolutely convergent. Okay, now you rearrange the terms in any fashion you want, the new series will also converge and the sum will be the sum of the original series. Okay, that is if summation an is said that summation mod an is convergent, then I know summation an is convergent. Let us call it the sum S. Now what do? You rearrange a1, a2, an, etc. in some fashion, get something new objects, b1, b2, bn, etc. and sum it bn, summation bn. That summation bn will also be convergent. Very interestingly, the sum will also be yes. Okay. Contrast this with the first example which I quoted. Okay. The series standard alternating series is convergent but not absolutely convergent. So that is why things fail there. Okay, this is why again one of the reasons why practicing analysis as a rule will pray that the series they get is absolutely convergent. Okay, therefore the life is much easier. Yeah, okay, let us get started. Yeah, this is the title of the lecture, Infinite Series 7, part of basic real analysis, and my email ID references as earlier my book on linear real analysis along with Dr. Ajit Kumar, and my channel remember YouTube. This is /C, that is for C for channel I guess, Kumar HCU. You may download the list of videos, and the list has a description and with the URL, and also it's arranged in an order of preference to learn. Okay, you can download it from here. Just look for list of videos, search for that. Okay, right. Now let us get to the business. So let us look at the series summation minus 1 to the power n minus 1 by n. Okay, and we have seen this is a standard alternating series. And it is convergent. Okay, we have seen it in the last lecture, but that it's not absolutely convergent. That therefore convergent but not absolutely. Okay, so maybe it's a good time for me to define. I have a series summation an. Okay, I say is conditionally convergent if 1, this is convergent, and 2, this series it's not absolutely convergent. That is summation an is not absolutely convergent. Okay, right. So the standard alternating series is one such a series. It's conditionally convergent. It's convergent but not absolutely convergent. Right. Now what I want to do is look at. So we know it's a sum is this is convergent. Let us say its sum is minus n minus 1. I claim s is not equal to 0. First observation. Okay, the sum is not 0. Why? You may recall the way we proved its convergence is by looking at the even partial sum CS2n. Right? Therefore, that we saw it's always positive. The first 1 minus 2 plus 1 minus 3 by 1 by 4 plus etc. 1 by 2n minus 1 minus 1 by 2n. Okay, therefore this is greater than half because this is already half, right? Therefore, and what is S? S is the LUB because we know S2n's are increasing sequence and this is LUB of S2n. Okay, therefore S is positive. In fact, it's greater than half, greater than or equal to half. Okay, but anyway, this is good enough for me. Okay, therefore S is non-zero. Is that okay? Pause. See, did you see something very interesting? As I keep saying, whenever I need the earlier result, I quickly go through the proof, at least some important steps of the proof. Just now I did how I proved alternating series is convergent. Okay, that proof is what we just like went through. Okay, anyway, right. Okay, now the way I want to rearrange is you group terms, groups of 3 terms. Okay, in which okay a positive term is followed by 2 negative terms. Okay, don't worry, I will write it and we will see that. So what are the series is 1 minus half plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 and so on, right? So what do I want to do? I want to rearrange. How do I rearrange? I group terms. I am going to take 1, let me just use a different color, 1 minus 2 and minus 1/4. Therefore it's going to be 1 minus 2 minus 1/4. This next one will be, I will be taking the other one, 1/3 and minus 1/6 and 1/7. Sorry, 1/8. Yeah, so the second term is going to be starting with 1/3 minus 1/6 minus 1/8. Okay, and what is the next one? I'm sorry if you may get bored, but it will be good to have those things. So this is going to be, the next one will be going to 1 by 5, and next will be minus 1 by 10, yeah, and minus 1 by 12. This is going to be, let me just, perhaps I should write that also. So 1 by 9 minus 1 by 10 plus 1 by 11 minus 1 by 12. So I'm going to take these things. One by 5, 1 by 10 and 1 by 12. I hope I am doing it correctly. Okay, you'll see that, and so on. Therefore, what will be the nth group? So do you see the pattern? This is 1 by 3, so this is the second group, and this is 1 by 5. Therefore, it is of the form 1 by 2n minus 1. When n is 3, this is 6 minus 1. When n is 2, this one. When n equal to 1, 1. Right? Therefore, that's going to be 1 by 2n minus 1. And let's look at this one. The first group is minus 4. That is, and this is minus 8. This is the second group, minus 8. Third group is minus 12. Therefore, this is going to be 1 by 4n. And what will be this? You just have to add this. This is going to be minus 1 by 4n minus 2. Do all of you agree with that? This is 4n. Yeah, do all of you agree? So this is the third term. Please pause, review, understand. Then proceed. Okay, right. Right. Now what do I do? Let us look at in each group of 3 terms. Okay, subtract the second from the first. Okay, what do I get? For example, here I have 1 minus half minus 1/4, therefore it's half minus 1/4. The next one will be 1/3 right? 1 by 3 minus 1 by 6 minus 1 by 8. So that is going to be 1 by 3 minus 1 by 6 is going to be 1 by 6 minus 1 by 8. So what is the nth term? Nth group? Nth group is 1 by 2n minus 1 by 1 by 4n minus 2 minus 1 by 4n. That is going to be 4n. Remember this is twice that. 2 times 2n minus 1 is 4n minus 2. Therefore, it is, if I take common denominator 4n minus 2, this will be 2 minus 1 by 4n minus 2, which is 1 minus. This is 1 by 4. You follow that? Therefore, the sum, okay, is going to be 1 minus half minus 1/4 plus 1/3 minus 1/5 minus, I think I am 1/5. I may make a mistake, 1/6, yeah. 1/6, 1/8 and plus 1 by 2n minus 1 minus 1 by 4n minus 2 minus 1 by 4n. This is going to be, okay, and so on. This is going to be, what are the terms now you can see? 1 by 2 minus 1 by 4, this is 1. Okay, the next one will be 1 by 6 minus 1 by 8 and so on. This is going to be 1 by 4n minus 2 and so on. Yeah, how many of you can recognize this? Notice that this is nothing other than half into 1 by 1 minus 2. This is half into 1 by 3 minus 1 by 4 and so on. This is half times 1 by 2n minus 1 minus 1 by 2n. Yeah, are you following? Therefore, this is nothing other than, if I add these things, okay, therefore let Tn be the nth, let T3n be the nth partial sum by the 3nth partial sum. So that is going to be 1 by 2 into 1 minus half plus 1 minus 1 by 4 and so on plus 1 by 2n minus 1 minus 1 by 2n. This is going to be nothing other than half of S2n. Do you follow that? Yeah, very good. So, but half of S2n, okay, yes, Sn converge to S, therefore, and S2n is a subsequent, therefore S2n will also converge to S, therefore this will converge to half of S, right? Therefore T3n converges to half of S. Right? Do all of you agree? Next, notice that the way I grouped, okay, yeah, okay, so what you have shown now? I have shown that T3n converges to T. Now, how do I know this series which I did converges? Yeah, notice that each of these things what I have done is these T3n's are all increasing. Yeah, so I claim, okay, therefore sum of this series, the new series, that is limit Tn is half of S, call it T. Therefore the sum of the new series turns out to be half of S. But remember, we only proved T3n converges to half of s. But what I want to say is the original series itself after this regrouping converges to this. So how do I know that? I hope all of you understand this. Yeah? Alright. So that is very easy. Okay, I leave it to you to check. Okay, so why does Tn converge? Okay, if Tn converges and since T3n converges to half of s, I know that Tn must also converge to half of s. Therefore, the sum of the rearranged series is half of s. And remember, s is not 0. Therefore, half of s is not equal to s. That is why I needed the fact s is non-zero. Yeah. I hope you understood this. Yeah. We are rearranging. Okay. There is only one small point which I have not explained. Namely, I have seen the partial sums of subsequent T3n converges to half of s. But why does the original sequence the partial sums Tn that must converge? If it converges, I am through. Yeah, please think about. Okay, have you figured it out? That is why I keep asking you always go back to the earlier case. Do you remember how we proved alternating series is convergent? We showed S2n's are increasing bounded above, therefore it converges. Then we also made use of the fact my ANs are positive, or I call it I think Tn. Okay, Tn's are positive, An equal to minus 1 to the power n minus 1 Tn. Tn's are decreasing to 0. That fact we used. Okay, therefore S2n plus 1 I can get from S2n by adding T, but for sign T2n plus 1, but that is going to be very small in absolute value because Tn goes to 0. The same way here, right? I know T3n, now I have to T3n plus 1 will be something to do with 1 upon 3n plus 1 or some such thing, but for sign. Similarly, 3n plus 2. So each one of them will be, I have to add to T3n to 1 or 2 more terms which are very small in size because 1 upon n decreases to 0. That fact you have to use. Okay, I hope you followed it. Do you want me to write? Okay, so why does it converge? So the obvious thing is, let us look at T3n plus 1. This is what I have. T3n plus 1 is I just have to add one more term. The one more term is going to be, see, what did I do? 4n minus 2n minus 1, therefore it's going to be 2n plus 1, right? This is going to be T3n plus 1 by 2n plus 1, right? Now where does it go? So this goes to s by 2, this goes to 0, therefore T3n plus 1 also goes to s by 2. Similarly, T3n plus 2. Okay, that is T3n plus T3n plus 1 term and one more term minus 1 by whatever that number 4n plus 1 minus 2, that term. Yeah, think about. So we get everything. Okay, so make sure you understand. Do not proceed unless you had understood this. Okay, let me just make sure I turn video is turned on. Yeah, you're right. Okay, now let's go to the next one. So now we want to talk about conditionally convergent series. Okay, so suppose an, okay, is convergent, but summation mod an is not convergent. Okay, we want to understand some important facts about this such series. So for that, what I will do is, suppose a is a real number, we will define the positive part and negative part. This is the maximum of a and 0. So if a is positive, suppose a is 4, then that will be 4 and 0. And if a is minus 4, then maximum minus 4 and 0, it will be 0. Do you understand? Therefore, a plus is always greater than or equal to 0, non-negative. So what do you think a minus? Remember a minus also, sorry, a, not a inverse. See, this is the problem, right? The moment I put a upper sign, okay, its tendency is put a minus 1. This is, look at the minimum. Suppose my a is minus 4, then minimum of minus 4 and 0 is minus 4, but then I take a negative, therefore it's a minimum of a and 0. Okay, do you follow that? Okay, and if a is 0, a plus or a minus, it's 0. Do you understand that? Okay, now what are the facts I want to know? See, when you go to higher studies, integration, Lebesgue integration, measure theory, etc., again you look at a function and real valued function, you will define the positive and negative part. Exactly, this is the same logic, so learn this well. That is why I said people who are not learn infinite series in depth have problem when they go for higher studies, especially in Lebesgue integration, etc. Okay, now you have seen a simpler example so that you know how to work with it. Okay, so let us look at this is a minus. Okay, now what are the things? What is the relation between a plus and a minus? And what is the relation between mod a plus and a minus? Okay, this is called the positive part of a, and this is called the negative part of a. This is just a name, right? Think of the number so that you know. So remember, even the negative part is a non-negative number. Remember that. Okay, this is also greater than or equal to 0. Because if a is negative, minimum of a and 0 will be a, therefore I am taking minus a, therefore I get a modulus. You follow that? So they are all closely related, right? Now what is this? See, notice that mod a is nothing other than a plus a minus. How many of you see that? Suppose a is positive, okay, then a plus will be a and a minus will be what? Minimum of a and 0 and negative. And since a is positive, then minimum is going to be 0, negative will be 0, therefore this is 0. Do you understand? And suppose a is a negative, right? Therefore this will be minimum will be, this will be a, this will be minus a in that case, whereas a, this will be maximum of a and 0. When a is negative, that is going to be 0, therefore it is 0. Okay, are you following? Therefore what do we have found? I have found mod a is nothing other than a plus a minus. And what is a? A is a plus minus a minus. Again for the same reason. Can you figure it out? Suppose a is positive, then I know a plus is a minus is 0, because this is minus of minimum of a and 0, therefore that is 0, negative, right? You follow that? Therefore yes. And suppose a is negative, then a plus is 0, because it is maximum of a and 0, therefore it's 0. And what is a minus? A minus is minimum of a and 0, that is minus a, right? Therefore minus of minus a will be a. I got it. Huh? Please feel confident. You should work out on your own. Okay, I am just doing it, but you should not look for this. You should do on your own. Okay, so let me write. Therefore mod a is nothing other than a plus a minus, and a is a plus minus a minus. Okay, understand this. This is going to be very useful for us. Okay, right, because we are going to play with. So now let's come back to the series an. So I am given a series an which is conditionally convergent. right? So what does it mean? Summation mod an is not convergent, but summation an is convergent, right? Okay. Now we want to do various things. Suppose an is convergent, right? Suppose an is convergent, or let's say mod an is convergent. Then I want to say mod this series is nothing other than summation n plus summation an minus. This is what first I want to make an observation. Do all of you agree with that? Okay. That is very easy. Why? Let us look at. Notice that an, we know that mod an is an plus an minus, and both are non-negative. Therefore, what is the relation between an plus and mod an? This. And what is the relation between an, the negative part? Mod an. Right? Because mod an is sum of these two things. Right? And therefore, since this series is convergent, okay, and this shows this series is convergent by comparison test. And similarly, this series is convergent. Do all of you agree with that? Okay. Now, since this is a series, infinite series convergent, this is infinite series convergent by algebra of convergent series, this series an plus an minus, okay, this is convergent and the sum is same as an plus an minus. Okay, let's recall what did we do, what I'm using. Suppose an is convergent and bn is convergent, then I know this series an plus bn, this is convergent and the sum is same as summation an plus summation bn. This is what I'm using, right? So this is convergent and this is convergent, the sum equal to this. But what is this? But an plus an minus is nothing other than mod an. Okay, so do you think I have proved it? So what have you proved? If summation mod an is convergent, implies summation an plus summation an minus are convergent, and summation mod an equal to summation an plus summation an minus. Okay, this is what we proved. Okay, pause, review, proceed. Okay, now let's go to the next one. Now what is an? Remember, I am still assuming mod an is convergent. Therefore, I know summation an is convergent. Right? Since summation mod an is convergent, we know that summation an plus and summation an minus, these are convergent. Therefore, by algebra of convergent series, summation n plus minus summation an minus is convergent, and we have summation an plus minus summation an minus is summation an plus minus summation an minus. But what is this? This is nothing other than summation a. Remember, we have shown that a is mod a is a plus a minus, and a is a plus minus a minus. So we are using that fact. Yeah. So let us recall. So if summation an is convergent, Then what are the things? 1, this is convergent or convergent, and 2, summation mod an is summation an plus summation an minus, and 3, summation an is summation an plus minus summation an minus. These are the 3 things we have proved. Okay, if you want, call it as a theorem. Okay, pause, review, proceed. So, but as I said, we are trying to deal with conditionally convergent, but what this theorem dealt with was absolutely convergent, right? So, what do I want to do? So, this is the next result. The next result is, suppose, okay, next result, let's assume an is convergent and summation mod an is divergent. Okay, then I want to say this is a series of positive terms, right? So I want to say this is, okay, both are divergent. In fact, okay, well, so it's a series of positive terms, non-negative terms. If it's not convergent, that is, if it's divergent, what does it mean? The sequence of partial sums is not bounded above, right? That is the sequence of partial sums of each of the series is not bounded above. Okay, I'm just recalling the definition, don't worry. Okay, so I want to prove this is divergent. Suppose it's not. Okay, prove. Suppose false. So with the loss of generality, let me assume an plus 1 is convergent. Right? Very good. So suppose an plus is convergent. Now let's look at a. What do we know? We know a is equal to a plus minus a minus. Right? Therefore, for each n, an is this. Right? Therefore, I have an minus is an plus minus an. Do you accept it? And now comes the trick. Now what do I know about the series an plus? By assumption, we assume it's false, therefore this is convergent. And what do I know about the series? This is convergent. Therefore by algebra convergent series, this series an plus minus an, this is convergent. Yeah, but that is not, that means, but this is nothing other than an minus, this is convergent. Yeah, because an minus is an plus minus an minus, right? Do you all agree with that? Okay. Please remember, we are using convergent series. We are being not algebra analysis. Okay, we are using all the fact. This is an plus is convergent, an minus is convergent. Okay, therefore what do I know? This an plus minus an minus, sorry, an, this is equal to this an plus minus an. You understand? That is what you are using. So this is convergent, but that is nothing other than an minus. Okay, we are using algebra convergent series, is not pure algebra. Okay, analysis is needed. Now, but we had already seen, therefore summation an plus is convergent and summation an minus 1 is convergent. Therefore this implies summation an plus summation an minus is convergent. But where does it converge to? This is equal to summation an plus an minus. But this is summation mod an is convergent. This is a contradiction. Yeah. So what have we shown? Similarly, so if what I have shown is if an is convergent, summation mod is divergent implies summation an plus is divergent, and similarly summation an minus is divergent. Exactly similar proof. Okay, right? This is the basis. Okay, this observation, this is a theorem, but I call it observation, is the basis for Riemann's theorem. What does it say? If an is conditionally convergent, and there exists a bijection sigma from n to n, so that let Bn equal to a sigma n, then summation, okay, and conditionally convergent, let alpha be a real number. Okay, then there exists a bijection n to n, so that this is convergent and it's equal to alpha. Please understand what it tries to say. Don't worry about the proof. I am not going to give the proof because the proof is, notationally cumbersome. It's essentially bookkeeping exercise. The basic idea is the series of positive terms, series of negative terms, both are divergent for a conditionally convergent series. That's a crucial thing. Okay, so what does it say? I have something like a1, an, etc. Now this may be some a sigma 1 may be my thing. This may be a sigma n. Okay, now I am adding them. Okay, this adds, let us say, is conditionally convergent, therefore the sum is yes, whereas this summation will be alpha. What is alpha? Any pre-assigned thing. You give me alpha, I can find a bijection. That is, this bijection is simply rearranging. Okay, what is the first term of the new series? Something like 100th term. Second term may be 12th term. Third term may be 27th term. And fourth term may be millionth term. All such things. So somehow I rearrange the term so that when I add them in the proper order. How do I add? In a sequential way now. b1 plus b2 plus bn, that is your tn, the nth partial sums. Now this tn converges to alpha. It's very important for you to understand the statement of the theorem. Appreciate it. Do not worry about the proof. Okay. Many people unnecessarily get into the proof, but you should understand this. Okay. That is where the next beautiful result comes, but that may have to wait because I'm running out of time. Okay, the beautiful result is this. Suppose summation an is absolutely convergent. When I say absolutely convergent, what does it mean? This series is convergent. Okay, right. Let sigma from n to n be any bijection let bn equal to a sigma n, then summation bn is convergent. Then, and this summation bn is same as summation an. So don't think of bijection, etc. What does it mean? Now you add a1 to an in any fashion you want. I may take a10 followed by a29 followed by a3 followed by a200. I keep on adding any fashion, right? Then the new series will be again convergent. Maybe it converges to different sum. No, it cannot happen. It converges to the original sum. What is it I have to do for that? I have to ensure the given original series is absolutely convergent. Do you understand that? This is a very beautiful result. That is the reason why a practicing analyst, okay, when he sees an infinite series, okay, if he believes in God, he prays, okay, let it be absolutely convergent so that it will be easier, okay. To prove it's absolutely convergent, he can use the standard test like comparison test, geometric series, or ratio test, root test, etc. They are the easy, or integral test. These are the easy tests. One can do that. Okay, learn this well. In the next session, I will prove this. Okay. So as I said, understand the Riemann's theorem, the statement thoroughly, and compare that statement with the last statement which I said, what I called as a beautiful result. If you have an absolutely convergent series, no matter in what way you reorder the terms and you get a new infinite series, you add them, the series will still be convergent and the sum will be the original sum. That is a very, very beautiful result. That is why absolutely convergent series are darlings of an analyst. Okay, we'll meet again.